So we're delighted to have today Ricardo Mendes from the University of Oklahoma to speak on the isometry group of spherical quotients.
All right, thank you. Yeah, so it's a pleasure to give a talk here in this seminar series. So I'd like to thank the organizers for giving the opportunity. It's very nice to see like the list of participants, some familiar names. I wish I could see you in person or something, but yeah, it's at least nice to see the names here and so on. I'll be talking today about isometry group of spherical quotients. So this is a project I finished recently. You can see it on the archive. And the idea is to look at the quotient of a sphere by isometric group actions and look at the metric space and look at what its isometry group is. Okay, so I'll start with just like this setup that I just kind of said in words here. Okay, so the setup is for us, G is going to be a compact Lie group, and V is going to be some Euclidean vector space, meaning finite dimensional real vector space with an inner product. And I'm going to see G as acting on V by linear isometries. In other words, we're given an orthogonal representation of this group, G on the vector space V, right? And whenever you have that situation, the vector space V gets partitioned into the orbits of the action, right? So each orbit is like, you take a vector and you apply all the elements of the group to it, and this gives you the orbit. They're all like pairwise disjoint, and they partition the vector space, right? So this is what I mean by orbits. I'm sure for 99% of you, this is all very familiar. And then we look at the orbit space, okay? So the quotient, I'll also call it the quotient. So this is, you just take the vector space and you mod out by this partition, right? So you identify any 2 points that are on the same orbit, right? And so you get this natural space, and you could also do the same thing with the sphere. Okay, so I'm going to use the notation SV for the unit sphere in the vector space V. So this is the sphere of radius 1 centered at the origin. And then we can, since the action is orthogonal, it preserves the sphere, right? And therefore, the group acts on the sphere as well. And we can look at the quotient of the sphere by the group. And the original quotient of the vector space is just the cone over that. So essentially, it's like the same amount of information, right? One is just the cone over the other. And we'll go back and forth between these two quotients. These are metric spaces, right? And on the sphere, I take the intrinsic metric on the sphere to get started. So we're talking about angles, right, as distances there. And the question I want to approach today is, let's study these metric spaces, the quotient, right? The V mod G or the SV mod G. And what is their geometry? What can we say about all kinds of geometric invariants of these metric spaces? And how do they relate to the representation, right? So from the algebra of the representation and the algebra of the group, right? So we have this, this is like the main question I want to approach to talk about today. And okay, so that's the setup. And then I also want to ask, why do we care about this, right? And well, there's like a few different angles, pardon the pun, for why do we care about this. One is if you care about groups acting on manifolds, let's say by isometries, then the local situation around an orbit is given by the situation by the slice representation, right? This is via the slice theorem, right? So the slice theorem gives you tubular neighborhood around an orbit. You describe it in terms of the slice representation. So if you can say something about these representations, and like even though it's just like a linear case, it tells you something that local about your manifold outside that, and maybe sometimes even global, right? Like we saw, for those of you who were here 2 weeks ago, Lee gave a nice talk in which like really key thing that he was doing was like proving some geometric results about the slice representations, the isotropy representations of tori, right? And extracting from that some global results about positive curvature and symmetry. So that's one reason why we care about, orthogonal representations. They give you a local picture for more general, like nonlinear actions. Another angle we can think about is that this is a nice class of Alexandrov spaces, right? So Alexandrov spaces, large class of metric spaces, very interesting to study. And this is a nice kind of subset of Alexandrov spaces, right? It's small enough class that you can say a lot about it. And it's large enough that, you're saying like interesting things that are non-trivial. So it's a nice kind of playground for Alexandrov spaces. A lot of like concepts from Alexandrov spaces, like space of directions, for example, you can see them very explicitly in this case, right? In this particular case. So it's nice to look at that from that point of view. And of course, there's like a natural like beauty of this subject. And I think the thing that attracts me to that the most is this nice interplay between algebra and geometry, right? So like the algebraic properties of groups and of their representations on the one hand, and the geometry of these metric spaces on the other hand, right? And this is, of course, a theme that I'm sure is familiar with to lots of you, right? Lots of times in this like symmetries and geometry, right? You're looking at this nice interplay between these two things. Okay, so that's like a little introduction. And let me give you like probably the simplest example that you can think of this interplay between algebra and geometry. This is a well-known result. I'm going to call it the baby example. And this is about diameter. So the point here is that, what's the simplest thing you can ask, simplest algebraic property of representation you can think of is whether it's irreducible or not, right? And for metric spaces, like maybe the most basic invariant of a metric space is its diameter, meaning the maximum distance between the 2 points. And these two things are related for this kind of examples in which the representation is irreducible exactly when the diameter of the quotient is less than pi over 2, okay? So here you can see, how algebraic property corresponds to geometric property of the quotient. I'm going to leave the proof as an exercise. It's very easy. This is a very well-known result. Okay, so let me move on to some more grown-up examples as part of my context here. Okay, so the next example is a shameless plug for a result that I was involved with from last year. So this is with Claudio Gorodsky and Christian Lange and Alexander Lichak. So what we proved is that the diameter, there is like a universal minimum value, or let's say a gap, right, for the diameter of quotients. Okay, in the sense that the quotient of the sphere by a group SV mod G is bigger than is either 0 when the action is transitive, right, on the sphere. But if it's not transitive, this diameter is always bigger than a universal constant epsilon. This universal constant doesn't depend on anything, on the dimension of the vector space or on the group. Okay, so there's a gap there, right? There's some values of diameter that are too small that never happen. And this, of course, you need to ask that the sphere has dimension at least 2. This is not true for the circle, as you can see easily. And so this is another example of like how we can say something about the geometry of the quotient. And the algebra comes into the proof of this, okay? So we use lots of stuff from representation theory, both of Lie groups, but also about finite groups. In fact, we have to use the classification of finite simple groups in the proof of this. So this is, I guess, as like, yeah, you cannot get less elementary than that, probably. There's like most complicated theorem ever, maybe, right? Classification of finite simple groups. We have to use that in this theorem. So that's another example of the interplay. And this came after a long list of partial and related results by many people. I'm listing some here: Jill McGowan and Sarah Greenwald, Catherine Searle, and Ben Green. But a bunch of other people were involved in results that are either partial or like in some special case, but more precise result, things like that, okay? All right. So there's another example involving the diameter, a bit of this general theme of like geometry of quotient and the algebra. And then there's a whole, I'm not doing like a survey here, right? I'm just giving you a few examples of some results along the same lines. There's a long list of classification results as well, in which you can think about it the following way. Let's impose some condition, some geometric condition on the quotient, and then let's classify all the representations such that the quotient has that property, right? And you can change the property and you have lots of interesting results, classification results like that. So I guess the easiest possible thing you can imagine is, okay, what's the, when is the quotient just 1 point, right? So this was proved by, this is a classic result of Montgomery and Samuelson and Borel. They give a complete classification of the transitive actions on the sphere. The result is actually stronger than this, but it implies this. And then you can also see in this kind of revisionist history here, you can see the result of Dadok, which is a classification of polar representations in this light, okay? The representation is polar exactly when the quotient is an orbifold of constant curvature. So Dadok classified all such representations, okay? So that the quotient is an orbifold of constant curvature. And of course, the case of where it's a manifold of constant curvature, this is the space forms, right? There's a whole book by Wolf about this. And then Brodsky and Lichak looked at the case where it's an orbifold, not necessarily of constant curvature. And they also have a full classification there. And finally, there's also the question of like boundary. Okay, so you can ask, when does the quotient have boundary? This turns out to be a rather special property of the representation. And in some work that's to appear by Gorodsky and Andreas Kollross and Burkhard Wilking, they give a classification in the case where the group G is simple and the representation is irreducible. Okay. All right. So this is just kind of to give you some context of, you know, people working on this kind of theme, right? Looking at the quotient, its geometric properties, and especially how it relates to the algebra. So the example that I want to look at today, the problem that I want to tell you about today is instead of looking at diameter or whether it's an orbifold or curvature or something like that, I want to look at the isometry group of the quotient, okay? So here's the problem that we're gonna be looking at. Given some representation of group G on vector space V, describe the isometry group. How do you compute this isometry group of the quotient, right? Okay, so let's start with some basic remarks about this. What does this look like? This isometry group. So first remark is that it's a Lie group. Okay. So more generally, the isometry group of any Alexandrov space is a Lie group. And this is a result of Fukaya and Yamaguchi from the 90s. And just as a little aside, just for fun, I can show you a picture of a metric space. I'm showing it to you on the on my camera. This is like a union of circles, infinite union of circles, all joined at the same point, and the radii is going to 0. The isometry group of this metric space is not a Lie group. It's actually Z mod 2 to infinity, and natural topology, compact open topology, is the product topology. So this group is homeomorphic to the Cantor set. Okay, so this is like to show you that, you know, this is still pretty reasonably looking metric space, but it's not a Lie group. Its isometry group is not a Lie group. But if you have Alexandrov space, then you're good. So that's our situation. So this is a Lie group, the thing we're trying to compute. Okay, so what's a natural source of isometries of the quotient? It is the G-equivariant isometries of the space V itself, right? So if you have G-equivariant isometry of V, it induces downstairs in the quotient an isometry, okay? And a natural question is like, how many of the isometries of the quotient do you get this way, okay? And the main result that I want to tell you today is that if you look at an isometry of the quotient that belongs to the connected component containing the identity of this V group, which is the isometry group, every such isometry lifts to a G-equivariant isometry of V. Okay, it's an element of the centralizer of the group in V. Okay, so so this kind of pretty trivial way of generating isometry of the quotient generates a subgroup of finite index of the isometry group of the quotient. Okay, so it generates in some sense most of them. That's the result I want to tell you today. So let me first tell you about trivial factors. So we're going to start assuming from now on that the vector space, the representation has no trivial factors, okay? So there's no fixed non-zero vectors on V, fixed by G, okay? Because if there is, well, then the quotient is just a product of some Euclidean space with the quotient of the part where G actually acts, and, whoa, what has happened? Anyway, and that's just kind of a trivial thing that's just kind of annoying. So I'm just going to ignore that. And if you don't have any trivial factors, then it turns out that any isometry of the quotient has to fix the origin, okay? The image of the origin under the quotient. So in other words, the isometry of the quotient of V by G is the same as the isometry of the sphere by G, okay? So this is a compact group we're talking about now, okay? So from now on, we're going to be looking at the situation. The general situation follows trivially from this, okay? All right. So I want to give you some remarks about this theorem, just to tell you like why we need some of the assumptions and so on, okay? Just to give you some context around the statement of this theorem. So I just copied the theorem here on the screen, just so that it doesn't disappear immediately from your screen. The first remark is, why do we need this correct component assumption, right? And the remark is that this is really necessary, okay? So you can find examples of actions where you have some isometry downstairs which does not lift, okay? So most trivial example is the following. Let's take the group G to be the product ON cross OM, and it acts by the product action on Rn cross Rm, okay? So the quotient of this is just the product of the quotients, right? Of Rn by On and of Rm by Om. Okay, so each of those is a ray, right? It's like 0 to infinity interval. So this quotient is just like the first quadrant of the plane, all right? And along the x and the y-axis there, you see the singular orbits. Okay, the singular orbits are Sn minus 1 and Sm minus 1, right? So what's the isometry of this first quadrant of the plane? I actually have a picture here. So I'm going to show it again on my camera, right? So there's the quotient is the first quadrant. The reflection across this y equals x line is the only isometry, only non-trivial isometry of this quotient, and it cannot lift because if n and m are different, this cannot lift because if it lifted, it would be an isometry of the sphere that sends some n minus 1 dimensional sphere to an n minus 1 dimensional sphere. If m and n are different, you obviously cannot have that. And if n equals m, on the other hand, it does lift, of course, then you can just take the map that swaps the Rn and Rm factors if n is equal to m. But this lift is not G-equivariant, okay? But it does lift in this case. So that's an example about the connected component hypothesis. But this last part of this example also shows you that there are some things that lift but don't live to G equivariant maps, right? And so you can go a little bit more general, right? You can look instead of the centralizer, right, the G equivariant isometries, you can look at the normalizer of G, right? So all the elements of ON that, of OV, let's say, that normalize the group G, they also induce isometries in the quotient, right? As the example above shows, you don't get in general all the isometries, even if you enlarge it in this way. But there is one special case where you do, okay? So if the group G that you started with was actually a finite group, then it's true that normalizer gives all of the isometries of the quotient, okay? This is covering theory for orbifolds. Anyway, I'll leave it as an exercise, but it's essentially just like existence of universal covers and the universality properties of orbifold covers. Okay. And finally, last remark I want to say about the statement of the theorem is that we cannot replace the vector space V with a general Riemannian manifold, okay? So you cannot have the same statement for a group that's acting by isometries on some general Riemannian manifold, okay? The counterexample here would be a torus with a warped product metric. So if you take a standard torus and then take a warped product metric, you lose one of the S1 factors in the isometry group, but you still have an S1 acting, and the quotient is still a circle. But the isometries of that quotient, the circle, they do not lift if the warping function is not constant, okay? So the picture here is the following. So I have here a picture on my screen, right? So you can look at the surface of revolution, and then you glue one side to the other. That's what I'm talking about. And then like the translation here, along this thing is not an isometry, right? If this function here, the radius function, is not constant. All right. So yeah. So anyway, I'm just addressing like why we need all the hypotheses. All right. Okay.
So what about if V is a manifold with constant curvature? Are there counterexamples?
Right. Yeah. So for the sphere, that's essentially what we're already doing, right? For Euclidean space is this as well, right? Any compact group will fix a point. And for hyperbolic space, I think it should also work. So it needs to fix a point, right? You take any orbit and you take the center of mass. And then you can see it acting on the tangent space there. And any isometry of the tangent space is an isometry of the whole, extends to an isometry of the whole hyperbolic space. So yeah, I think it works there too.
Thanks.
Yeah, sure. Yeah, I don't know about, for example, symmetric spaces. I think it might be interesting to look at that question. More general symmetric spaces. But yeah, okay. All right. So, okay, so now let me tell you about some corollaries of this result. So, I just copied the result again at the top of the screen. And one corollary is that it is a structure result for this isometry group of the quotient, okay? So, recall that in general, right, there's a general fact about compact Lie groups, is that up to cover, it's a product, so connected, right? Connected compact Lie group. Up to cover, it's a product of a torus with some simple compact, simply connected Lie groups. And those are classified, right? There's classical type and the exceptional type, right? Classical type A, B, C, D, and then exceptional type E, F, G, right? And the result here is that this particular compact group we're talking about, the isometry group of V mod G, connect component, is always a compact group of classical type. In other words, up to cover, when you look at this product into simple factors, you'll never see any exceptional factors. You're only going to see the classical factors. So SUN, spin-ends and spn-ends. Okay, so G2 is never the isometry group of a quotient, okay, of a spherical quotient, or it never appears as a factor in such a group. That's one corollary. Another corollary is like, let's look at the case where V is irreducible. So if the representation is irreducible, then this isometry group is actually very small. It's ranked at most 1. We can say more explicit things about it, and maybe I'll do that in a moment. But for now, you know, the rank is at most 1. So it's like a dimension at most 3. Okay. All right. Okay, so now let me move on to Schur's lemma. Okay, so I want to understand more explicitly how can I actually compute the isometry group of the spherical quotient. First, let me rephrase the main theorem in the following way. So let's denote isometry subscript G of V as a set of G equivariant isometries. This is the centralizer of G in OV. Okay. Then we have a natural map from, let's call it P, this natural map, from this group of G equivariant isometries to the group we want, which is the isometry group of the quotient, right? It's the induction, right? In each G equivariant upstairs induces an isometry downstairs. That's this map. And then the theorem that I just mentioned before can be rephrased as just saying that this map is surjective. Okay, this is a group homomorphism and it's surjective. So this tells you kind of what we need to do to compute this group, right? Let's say up to isomorphism. We need to, 1, identify what the group of G equivariant isometries is, and 2, what's the kernel of this map, right? If you have those 2 things, that gives us the isometry group that we want, right? The quotient. Okay, so first order of business is how do you compute this group of G equivariant isometries? And turns out this is very easy, and it's an application of Schur's lemma. Okay, so how do we compute this G equivariant isometries? Via Schur's lemma. You start with a vector space, and you break it into irreducibles, irreducible G representations. Okay, let's call them V1 up to Vk. Each one of those has some multiplicity. Let's call them N1 up to Nk. So what we're assuming here is that Vi and Vj are not equivalent, right? They're inequivalent representations. Then, if you apply Schur's lemma, you're going to see that the isometry group of the quotient oh, sorry, this is a typo. I meant to write the G equivariant isometries. Okay, so where you see isometry group of the quotient, you look at the G equivariant isometries. Sorry about that. This is actually the product of groups HI, where each HI is like one of those groups, either SONI or UNI or SPNI, and that depends on the type of the group of the representation VI. Okay. So what do I mean by type? Representation, an irreducible real orthogonal representation can be of real type or complex type or quaternionic type. And that is the following, right? You look at the endomorphisms, the G equivariant endomorphisms. It's an associative algebra, and by Schur's lemma, each non-zero element is invertible, right? So this is an associative division algebra, which we know from classic algebra, that can be only like the reals or the complex numbers or the quaternions. That's the type of the irreducible representation. And according to the type, you get this, one of these groups, all right? So the big group there, the equivariant isometries of V, is a product of groups like this, right? And from this, we can see that the corollaries that I mentioned before, they follow immediately, right? Because now, like, for example, the fact that it's a group of classical type, well, if you take a product of groups like SON, UN, and SPN, and you mod out by a normal subgroup, you're only going to see factors of the same type, right? Torus, SONs, UNs, and SUNs, and SPNs, right? So, so that's clear. And the other one too, right? If V is irreducible, then you only have one of these representations, and the multiplicity is 1, right? So it's going to be a quotient. So if the representation of real type, then this is going to be a trivial group. if it's a complex type, it's going to be either a circle or the trivial group. And if it's quaternionic type, you're going to see either SP1 or SO3 or the trivial group as the isometry group of the quotient, the identity component. Okay, so you get this immediately, right? Okay, so that's great. But now let's move on to like how do we actually compute the kernel now? What can we say about the kernel, right? The first step in our computation was to compute this large group, right? The equivariant isometries. That's what I just said now, Schur's lemma. So the next step is, what about the kernel, right? How can we compute it? Okay, so I just copied again the rephrasing of the main theorem here. P is what I'm calling the map that induces isometries downstairs. What can we say about the kernel? So let me give you an example to start with, okay? So let's look at one representation that we all know and love, and that's the Hopf-action. So here we have the circle acting on R4, okay? And this, as a representation, is a sum of two copies of the same representation, namely you take S1 acting by rotations on R2. So if you take two copies of that representation, that's the Hopf-action we're talking about. And this representation V1 that I'm calling here is a irreducible representation of complex type. So from the discussion I was mentioning before, the G-equivariant isometries here is U2, okay? The group U2 is the group of all G-equivariant isometries. Okay, that's great. But, well, we know exactly what the quotient is, right? So we also know the quotient of the sphere by the Hopf-action is just the sphere of radius of two-dimensional sphere of radius 1/2. And so we know what the isometry group of that is, right? That's okay. There's a little typo there. I should have put identity component of that. That's SO3. Otherwise, it's O3, right? But the identity component of the isometry group of the quotient is SO3, which is also PSU2, right? And in this case, the kernel of that map there is exactly the center. Okay, so that map that induced, the inducing map from like G-equivariant isometries to the isometry of the quotient is exactly the quotient of U2 by its center. All right. So when you mod that out, you get your SO3 as expected. And it turns out that this example is typical. Okay, so most of the times this is what happens. Okay, so maybe I should mention also that this is not only the center of U2, but it's the center of the group G as well, right? Okay, which is a billion, right? So it's the whole group G, right? So that's why, in some sense, you see some kernel in this map. The point is that the group itself, of course, acts trivially in the quotient, the group G, and if the group G has part of it inside the G-equivariant isometries, which is the case here, it's completely contained in the group of G-equivariant isometries, then of course you're going to have some kernel, right, in this map. Okay. All right. So what else can we say about this? So I just copied the rephrasing of the theorem again, so it doesn't disappear from your screen. And here's what you can say in general. Okay, the situation, the Hopf-action, the kernel, the center of the group G, the original group G, is part of the kernel, right, of that map P. That always happens. Okay, anything that's in the center of G commutes with all the things in G. Therefore, it's a G-equivariant isometry, right? And it doesn't act downstairs, so it's in the kernel. And this is the typical case in the sense that if it's larger, okay, so if the kernel strictly contains the center of G, then what do we have, right? Then we have the following situation. We have the group G and the group G cross kernel of P. They are acting with the same orbits, right? Because kernel of P is not acting at all downstairs. So G and G cross kernel of P are orbit equivalent. And since this is larger, right? G cross kernel of P is larger, strictly larger than G. That's what we're assuming. That means that this G cross kernel of P, it must have non-trivial principal isotropic groups, right? And so what that means is that you can take a reduction, right? You can look at the fixed point set under the principal isotropic group, and you can do what's called Luna-Richardson reduction, right? So this is what I'm writing here. V mod G limits a reduction, okay, in the sense that V mod G is equal to the quotient of some smaller vector space by some other group action, right? The smaller vector space is the fixed point set of the principal isotropic group of G cross kernel of P. And in particular, you also get out of this that the quotient V mod G has boundary. Okay, so here we're linking back to something I mentioned at the beginning. And this is by Wilking, right? Wilking has proved a while ago that if you have non-trivial principal isotropic group, then the quotient has boundary, okay? And if you remember, having boundary in the quotient is a pretty special property. So in some sense, this is the atypical case, okay? That you have a bigger kernel of P than the center of G, okay? So let me give you probably the simplest possible example of this case, which is the following. Let's look at the group SP1 and acting on R4, okay? R4 I'm identifying here with the quaternions, and this is acting by left multiplication, right? So this is a irreducible representation of quaternionic type. So if you go back to our slide about Schur's lemma, it tells us that the G-equivariant isometries is just SP1. But what SP1 are we talking about here is the SP1 that acts on the right, right? This is the by right multiplication. And of course, the quotient has no isometries at all, right? The quotient is just, so this action is transitive on the sphere. And so this has no isometries in the quotient. And so the kernel of P is everything, right? It's the whole SP1. And that's what's happening here, right? You have boundary, you can see here the boundary, right? You can see that it limits a reduction. It's just like R mod Z mod 2. And you can see also that you have this larger group, which is orbit equivalent to it, right? Namely SP1 cross SP1 acting on both sides. In other words, SO4 acting on R4 is larger group with the same orbits as the SP1 group, right? So, and that has non-trivial principal isotropy, right? That's Z mod 2 cross SO3 as the principal isotropy there. So this is illustrating this last proposition. So this is like a typical case. The typical case is the kind of like the hop faction. All right. Okay. So so in the last few minutes, I think I'm going to end up finishing slightly early, probably. Let me tell you a little bit about the proof of this theorem. Okay. So to talk about the proof, we need to talk about the concept of the smooth structure of the quotient. Okay, so so far we have been looking at the quotient V mod G as a metric space, but of course it has much richer structure than that, right? It's stratified space and so on. But another piece of structure that it has is its smooth structure. Okay, so what do I mean by that? We select a subset of a set of real valued functions on the quotient and call them the smooth functions. What are they? And this was introduced by, I think, by Jerry Schwartz. The smooth functions are exactly the functions on V, which are G-equivariant and smooth on V in the usual sense. So in other words, they are the function of the quotient such that when you pull it back to V, it's a smooth function there. Okay, so that is the set of smooth functions. And then we can define, now suppose we have two quotients, right? V mod G and W mod H. V and W have nothing to do with each other. The groups have nothing to do with each other. These are two quotients, completely separate. If you have a map between them, we say that it's a smooth map when it pulls back smooth functions to smooth functions, right? In the sense above, okay? So that's a notion of smooth structure that this thing has, that the quotient has. And now the proof of the theorem, the main theorem from the stalk, is I use the results, two results about smooth structure. The first one, oh, sorry, before I get into that, I can't really resist talking about the Alexandrino-Lichak conjecture, which is about this stuff, namely that isometries are smooth, okay? So this is an open conjecture. Is it true that if this map is an isometry that I wrote before, is it always smooth, okay? So this like would generalize lots of interesting things, like Chevalier restriction theorem, the Luna-Richardson theorem, stuff like that. Anyway, this is an open conjecture about this stuff. But now let me mention two theorems that I'm going to use and that relate to the smooth structure of the quotient. One is by Alexandrino and Marco Hadesky from 2017, and it says that the connect component of the isometry group of the quotient, the action of this on V mod G is smooth, in the sense that the action map, right? Isometry group cross V mod G to V mod G is a smooth map. Here, this is the identity component, okay, of the isometry group. So they prove that this is smooth in the sense that I wrote before. And that's one of the results. And the other result that I need is by Jerry Schwartz from 1980. And it's about isotopies. So he has shown that any smooth isotopy of the quotient, okay, smooth in the sense above, starting at the identity, lifts to a G equivariant isotopy upstairs, okay? Smooth isotopy upstairs. So you have these two things together, okay? One, the isometry group, the connect component isometry group acts smoothly, and the other one, if you have some smooth isotopy, you can lift it to a G equivariant isotopy. If you just take these two things together, what you get is the following. So let's start the sketch of the proof, right? Start with an isometry of the quotient that belongs to the connect component of the identity. You can connect it, right, to the identity, right? So you can, it's the end point of a smooth isotopy. And therefore, since the action is smooth and you have the smooth lifting, this like lifting of isotopies by Schwartz, if you just put the two things together, we get that this isometry we're starting with here, phi, it lifts to something smooth, but so it lifts to a G equivariant diffeomorphism of the vector space that fixed the origin, okay? So we have a lift, it's just not an isometry yet, right? So all that we have to do right now is to promote this lift to an isometry, okay? So we have a diffeomorphism already, we just want to make it an isometry. And the claim here is that actually the simplest thing you can imagine works, namely the differential of this diffeomorphism at the origin, that's a linear map. That is your isometry lift, okay? So why is that? And by the way, I'm writing here sketch of proof, but this is actually the whole proof. So why does this work? So the point here is the following. Downstairs in the quotient, since phi is an isometry, it commutes with homothetic transformations. Okay, the homothetic transformation I'm calling R lambda here in the slide. So if you take lambda real number and you look at multiplication by lambda, you have that map on V and it goes down to a map on V mod G. And downstairs in the quotient, it commutes with the isometry, right? The isometry must fix the origin, okay? So it commutes with homothetic transformations. So what that means is that if you take now your diffeomorphism phi tilde and you conjugate it with homothetic transformation, that's a different equivariant diffeomorphism, but it's a lift of the same isometry downstairs, right? That's great because now, of course, we just so that's what I just said, right? The conjugation lifts the same isometry started with downstairs, because downstairs it commutes. Oops, sorry. And then of course you can just take, oh, I should have put one more bullet point here. Now of course you just take the limit, right? You just take the limit of lambda going to infinity, and that will give you exactly the differential at the origin, right? It's a limit of conjugations with homothetic transformations. Okay, that's what I wanted to do. So thank you very much for your attention.
Let's thank the speaker. Are there questions?
Hi, Ricardo.
Yes.
I'm a little bit confused by the last slide.
Mm-hmm.
Can you go back to the previous slide?
Oh, yeah, sure.
Well, what is this R lambda?
So R lambda is what I'm calling the multiplication by lambda as a map from V to V.
Uh-huh.
It just takes a vector and multiplies it with lambda.
Okay. Wait, phi tilde is not necessarily linear, right? Otherwise, this is always cancels out.
Right. Phi tilde is a diffeomorphism at this stage.
Okay.
Yes, you're right. It's if phi tilde was already linear, this would not do anything to it. But this is some diffeomorphism. So when you take the limit of this conjugation, what you get is exactly the differential at the origin.
Okay.
Are there other questions?
I have a question. Do you hear me?
Yes.
This is Karsten. Why do you say that the no boundary is the typical case? Because to me, I always felt it the other way around.
Okay. This is not a very precise statement. It's a bit of a vague statement. But for example, there is this classification that's going to come out soon of all the irreducible representations of simple groups such that the quotient has boundary.
Okay.
That, and it's a restricted list. I don't know if you can make a more precise, some other precise statements. Maybe you can also do that. Like if you just fix a group and look at all its representations, maybe you can say that possibly, you know, if the highest weight is large enough, it's not going to have boundary in the quotient or something like that. I feel like there could be some statements like that too.
So that's a classification theorem, just a list of groups, not a uniform description?
It's a list of groups. It's not my classification. This is by.
Well, I understand, yes.
Yes.
But there's no geometric descriptions of which ones do and which ones don't.
I don't know exactly. I think it's a list. I think it's really a list.
Okay.
Yeah, but only for simple groups, right?
Oh yeah, we have now one of the authors of that here. Yes. It's, if I'm not mistaken, simple group and irreducible representation, right?
Yeah, for no. Can be
No?
reducible, doesn't matter. Irreducibility is not necessary. But simple groups, because if the group is semi-simple, then it's impossible to write a list. There are too many cases.
Okay.
Can produce too many examples. Maybe you could write a case, in the semi-simple case, you could write a list for irreducible representations then.
I see. Okay. Is that going to be on your paper too?
The second one, no.
Sorry to put you on the spot here.
Do you assume the groups are connected?
Yes.
Okay.
Connecting groups, right.
Are there any other questions? If not, let's thank the speaker again for a nice talk.